Alrighty. Alright. Looks like it's gonna be a hard one today. Maximum number of points from grid queries. You're given an m by n integer matrix grid and an array of queries of size k. Okay. Find an array answer of size k. So each query has that answer. Such that for each integer query set I, we start at the top left cell of the matrix and repeat the following process. Queries at I is strictly greater than the value of the current cell that you're in. Then you get that if queries at I is strictly greater than the value of this current cell that you're in, then you get 1 point if it's the first time visiting the cell, and you can move to any adjacent cell in the 4 directions, up, down, left, right. Otherwise, you do not get any points, and you end this process. Okay, so after the process, answer I is the maximum number of points you can get. Note that for each query, you are allowed to visit the same cell multiple times. Query size strictly greater than the value of the current cell that you're in. And then you can get 1 point if it is your first time visiting a cell, then you can move to any adjacent cell. Or you can move to the adjacent cell multiple times. Or you can visit a cell multiple times. Okay. Maximum number of points you can get. Huh. Okay, so you can only visit something once, I see. And you only get the point if you visit the first time. Alright, so there's 3 queries here, and the queries are 5, 6, and 2. I think you always start, you start at the top left, and then you can go to 1 goes, well, everything that's less than 5 that's connected to this thing is these cells. So therefore there's 5 points. And then everything that's connected that's less than 6 are these cells. So that's 6 points, and then everything that's less than 2. And that's only that. Here queries is 3. You start with the 5, but you can't really go anywhere because 5 is bigger than 3. Okay. Alrighty. Seems reasonable. So for traversing 2D arrays like these, you generally don't want to use a graph, although you could. You can say that for each node, the neighbors you can graph the neighbors, but you generally have just I generally have a delta array, and it's going to have the the change in row and change in column for movement. So like 0, 1, 0, -1, 1, 0, and -1, 0. And and you'll probably want to have a row and columns. Rows and columns equals the length of the grid and the length of grid's first array. So it seems very similar to finding islands, because everything is connected and you can only move to your connected as long as the value is less than the query value. The only issue is there might be a lot of queries, and you really don't want to make a new traversal each time. So how do you determine how much you can go? So you could sort the queries by lowest to highest. The number of queries is k, where k is 10 to the 4th, so that's pretty fast. And if you sort the number of queries by lowest to highest, then you can slowly expand out your borders of your island, I guess. So maybe queries.sort. I feel like this is probably pretty fast. By sorting shouldn't take that long, especially compared to traversing maybe 1,000 by 1,000 matrix. Okay, so I wonder. Yeah, sorting seems fine. 1,000. I wonder if I should sort by wonder if, no, all right, let's just keep going. So for each, so we're assuming that they're increasing value like 2, 5, 6. So if it's a 2, then let's go ahead and set a, how do we want to do this traversal? I guess maybe scene is a set, and let's say the initial row and column that we're at. We probably need some sort of data structure to keep track of kind of the boundary or the nodes that we need to, the spots that we need to evaluate. So I'm gonna, this feels like maybe, is it a queue? Maybe a deck? Double-ended queue? Do I care about traversing it in lowest numbered? Probably. Yeah, maybe a deck is what I want. Okay, so let's say I have a deck, a double-ended queue, and it's going to start with 0, 0. You know, I think I'm going to try for one optimization here. I'm going to sort based on I want to keep track of where the query was. So no, I guess that's fine. Okay. So for each no, while there is a deck, while deck and so the deck contains the nodes that I want to evaluate along with where I am at in the query. So maybe I should be going through the queries. So for each query, I'm going to have a Q map as well. And that's going to be maybe a default dictionary. So for each query, Q and queries, I'm going to say that as long as it's not quite right. I think I need not a deck, but a heap. Because I kind of want to traverse to the lowest numbered neighbor if possible. So the heap has information about the current node's row position and value. So, and it's going to sort based on the value. So it's going to make grid at 0, 0. It's going to be tuple of the value and the position. Yeah, I think a heap is what I want. So for each query, I'm going to see if the heap has a value that's lower than that query. So I'm going to peek into the heap and not actually take away from the heap. And heap is just going to be like something that keeps the elements, but also has at its front the lowest valued element, the lowest valued grid number, grid value. So if the query is greater than heap at 0, the zeroth value, the heap at 0 is a tuple, and the 0 is the value of that tuple. Then I can, is it if or while? I think it might be while. And I guess right now I need to have a counter. While that's the case, then I'm going to take it from the heap. So heap q dot heap pop this heap and then increment the counter. And also say that for each neighbor, so I'm going to go through the neighbors, which is going to be for each change in row and change in column in the delta array. The new row, new column is going to be equal to actually, when I pop it, I need to actually get the value. It's going to be the value, the row and column of this node is popped. And then the new row, new column is going to be row plus dr, column plus dc. And just as a simple thing here, I'm going to have a function to make sure that it's a valid spot. So return whether or not this row is between 0 and less than row less than number of rows, and column 0 is less than or equal to column less than calls. So if it's a valid position in the matrix, and also this thing hasn't been seen yet, so nrnc not in seen, then scene.add nrnc. I could maybe have a 2D matrix for the scene rather than a hash. And then I'm going to add onto the queue the position of this. So the value in the position. So grid at this new row, new column, this position. Okay. And I think that's it. And then after I do all the, after I process everything in the queue that could be, that is smaller than the query, then I'm going to just say that the answer to this query is this value. I'm just going to have a queue map, which is going to be a default dictionary, and the queue map for this value, for this query, is equal to this count. I think queries needs to be copied over because this is not the original queries. Or this is, yeah, the order is different. So I'm going to say queries queue copy is equal to queries sorted queries. I think sorted queries. I think that returns a copy of the array. Returns a new sorted. Okay, yeah. So I need to go over the queue copies for the queries. Queue copy. And after that, I'm going to go answer equals the array. And for each original query, so queue and queries, answer.append the mapping for this query. Queue map for this query. Okay. I think scene should actually start with 0, 0. How is it going to work? Scene is the set. I think it looks like that. 0, 0. Okay. So goes through, sort the queries, has a heap that tracks the lowest value, goes through every sorted query. I'll say queue sorted. For every sorted query from the smallest to largest, the actual query, if it's bigger than whatever is the smallest current kind of border, then while that's the case, take it out, increment the count of how big the island is, and move to the adjacent ones that haven't been seen. If haven't been seen, add it to the query and make it seen. Set it to be seen. After that, you've gotten your maximum size of the number of things that you move to. So you map it, map that query to store that value, and then, yeah, turn the answer. Queue push. Oh, heap queue needs to actually say what the heap is as the first parameter. Okay. Ooh, index. Whoops. While there is a heap. While heap. Okay. Solved. Not very fast. I think a couple things. One is I could use a 2D array for the scene set. So I'll say scene is equal to false times false times the number of columns for each row for k and range of rows. And I'll just print out scene here just to make sure that this is doing it right. So it's a 3x3, and that's correct. It's a 3x2 or 2x3. That's correct. Okay. And then using that rather than the hash, rather than the set. And technically scene of 0, 0 is going to be true. It's valid, and scene at this index, and R and C, and it's not seen in that spot. Then scene at this spot is true. All right. Okay, better. Still not fast enough. What if I did a map instead of doing a map for this? What if I just did an array? It's 10 to the 4th, so I mean at most it could be 1,000 as your query values. So I guess I don't know if you actually need to sort. Queue and sorted. So okay, let's see if you don't. Let's say you just used 0 times the maximum. Let's say Q max is going to be maximum of the queries. And you multiply by the Q max plus 1. Well, once you sort it, you can just say that Q max is the last element of the Q sorted array. Yeah, so if it's 100, you need 101 elements if you don't want to offset it. And then Q map Q. Okay, I think this is changed. Q sorted -1. Yeah, it's not maximum function at all. Alright, that was even slower than before, I think. Yeah, and it was more memory. Um, hmm, how to make this faster? I guess, yeah, I guess the mapping was just faster than that. Guess you don't need a default dictionary. You can just use the dictionary. Yeah, you can just use the dictionary here. QMap is just a I don't know if that's any different. A default dictionary versus a regular dictionary. Yeah, didn't really make a difference to me. I guess it lowered the memory back down to what was before. Huh. I think maybe the slow part is actually the heap. You make a tuple for the heap. You make a tuple for the heap. It can't be that slow, can it? So you go through your queue sorted. I guess what you could do here is you can make the queries into a set and then make it into sort it, because then you don't have if you have duplicates, then you don't have to worry about sorting the duplicates. Alright, that still didn't do very much. So there's 79%. Something I might be missing. For each, while you do your sorted array, doesn't take that much more memory to sort. Like you could do hmm qmap qmap q. I mean, even if this is not strictly the fastest, this is pretty darn reasonable. Can you do you need to have seen? I think you do. Yeah, I'm pretty sure you do. Like you need to prevent yourself from going back to the same spot as before. And pretty sure you need a heap. If you kept track of your boundary and then you just if you kept track of your boundary And so your boundary is initially 0, 0. And your boundary is a so if you kept track of your boundary is just initially one element. And then you have a certain threshold for that size. No, there's you either consider, so currently I'm not keeping track of the boundary at all. No, I am keeping track of the boundary, no. The heap is my boundary. Every element in my heap is a possible new spot. Yeah, the heap is the boundary. And then as my queries increase, interesting. All right, well, I think this is good enough. All right, I'll maybe play around with this offline. But okay, summary. This is use a heap to keep track of nodes, particularly the value, and the row and column of boundary, and heap will allow access to, or quick access / identification of lowest value. Go through the queries sorted order, and as you increase the query size, then you might increase the boundary of your island of values that are smaller than that query. For each remove from heap, which is, again, each time you're removing is the lowest value, that are below the query, and increment the counter. Keep track of query to count using a map, like I use a dictionary. And then finally, create answer array using the map. Because if you have the query sorted, then you need to keep track of what the actual original query was in terms of the index, where that query was, and then the index into the map, into the answer array. Time complexity, this is going to be pretty fast. You go through, this is O of n times n, the size of or m, n are rows and columns. You have a scene matrix that prevents you from backtracking. So, and you're going through each element pretty much once. Like you pop into the array or into the heap, and then you remove it from the heap at some point. So there's you're not duplicating that. base complexity. This is going to be this is also O of m times n possibly. How big can your boundary be? I mean, you have a scene thing that, yeah, it's the size thing. O times n times n. You do need to keep track of the where you've been, and then the heap can grow pretty large. Can match, or it can match at least like one dimension of the m and n. So it can be maybe m plus n, which I guess is, yeah, m plus n is kind of the largest the boundary size could be. Is that true? Yeah, m plus n. Alright.